Okay, now it should be working. Yeah, yes, we're live. Okay. Okay, then welcome everyone to the new lecture on PNS DRAM Bender. And in this lecture, Giray will talk about his recent work, HiRA, hidden row activation for reducing refresh latency of off-the-shelf DRAM chips. And without further ado, I will leave the stage to Giray, and I will interrupt him to ask questions if there's any on YouTube chat. So Giray, you can go ahead, please.
Okay, thanks, Ataberk. I hope my screen is still visible. Okay, hello everyone. My name is Giray Yaglikci, and today I will talk about this paper that Ataberk already mentioned the name, and you already see on the screen. And so I'm a PhD student in Safari Research Group, and this paper was published. I'm the first author in this paper, and we presented it in about a month ago in this year's micro conference. Okay, so I hope this paper will give a nice example of how we use DRAM Bender. This is not the only paper, of course. We use DRAM Bender or SoftMC. So I will start with an executive summary. So you might be unfamiliar with some terminology here. Don't worry about that. I will provide the necessary background after this. So in this paper, the problem we tackle is DRAM refresh, and in particular, the increase in large performance overhead of DRAM refresh. So DRAM refresh is a fundamental operation in current main memories, and it is there to avoid bit flips that can happen due to charge leakage. And as DRAM technology density scaling goes on, we observe that the performance overhead of this DRAM refresh increases significantly. So in this paper, our goal is to reduce the performance overhead of DRAM refresh in future DRAM chips. And our key idea to do so is to hide the refresh latency by refreshing a DRAM row concurrently with activity in another row in a different subarray of the same bank. And to do so, we propose a new operation called hidden row activation. In short, it's HiRA. And what HiRA does is it issues DRAM commands in quick succession to concurrently open two rows in different subarrays of the same bank. And we experimentally demonstrate that HiRA works on real off-the-shelf DRAM chips by violating some timing constraints, and it significantly reduces the time spent for refresh operations. To use HiRA effectively, we also propose a mechanism called HiRA Memory Controller, and HiRA Memory Controller basically leverages HiRA to perform refresh requests concurrently with DRAM accesses and other refresh requests. And by doing so, HiRA Memory Controller significantly improves system performance by hiding refresh latency for both regular periodic refreshes and the refreshes that are used for preventing RowHammer bit flips. So with this quick recap, I'll just continue with some background and problem definition. I will give a little more details about the terminology that I talked in the previous slide. So let's start with DRAM organization. So this is a DRAM module, what you see on the screen, and it is used as the main memory in many computers and systems today. So within the DRAM module, a set of chips form a DRAM rank, and within a DRAM chip, we have multiple banks. And each of these banks consists of multiple subarrays. And within every subarray, we have a two-dimensional structure of DRAM cells. that are organized as an array of DRAM rows, and these rows are accessed using word lines, and these cells are connected to a structure called row buffer via bit lines. So when we want to access data inside DRAM chips, we access it in row granularity. So we first activate the row, or in other words, we fetch the row's content into the row buffer that contain this data that we want to access. And then we perform some column accesses for reads and writes, and these are serviced from the row buffer structure. And then in order to access data in another row, we need to precharge the bank, meaning that it closes the row and prepares the array for the next row activation. So DRAM internally is a leaky mechanism, not mechanism, sorry, it's a leaky circuit. So DRAM cells store data in terms of charge on the capacitor, on a capacitor, and they tend to leak over time. And to avoid losing data due to this charge leakage, we need to periodically refresh these DRAM cells. And therefore, it is a key maintenance operation in DRAM. So what DRAM refresh does is it basically activates a row and then precharges the bank. And by doing so, it restores the charge in the DRAM cells. That's the refresh operation fundamentally. So there is one problem that DRAM refresh, during the DRAM refresh, we block the whole bank or whole rank so that no other accesses can be performed to the DRAM bank or rank during a DRAM refresh. And it comes with a performance overhead, of course. So before talking about performance implications, I want to introduce two types of refresh that we have today. The first type is what I actually explained one slide earlier. So it is called periodic refresh. What it does is it periodically restores the charge that a DRAM cell leaks over time. And the second type of refresh is relevant to a read disturb mechanism in modern DRAM chips called RowHammer. So I need to give a little bit background about RowHammer. So in modern DRAM chips, due to density scaling, when you repeatedly access a DRAM row, it can cause bit flips in other physically nearby rows. And this is basically a read disturb mechanism. And to avoid these kind of bit flips, a common method is to perform an operation called preventive refresh. And you basically just refresh the rows that are nearby a frequent access row so that those rows will not experience bit flips. So this is the second type of refresh, preventive refresh. So when we look at periodic refresh with increasing DRAM chip density, we see that with increasing DRAM chip density, now we have a larger capacity in a chip, and therefore it has more rows to be refreshed. And at the same time, we have smaller cells now, which means that they store less charge and they might need to refresh more frequently. So here is a plot where we sweep the DRAM chip capacity on the x-axis and investigate how the performance overhead of DRAM operations change over time. And we observe that as we increase DRAM chip capacity, we need to spend more time on performing these periodic refresh operations, and they incur a larger performance overhead. So things are getting worse. When we talk about the preventive refreshes, we also observe that actually there's a lot of evidence in the literature showing that RowHammer vulnerability worsens as DRAM chip density increases, and this is because the DRAM chips get close to each other and they become smaller. And when we look at the experimental data in the literature, we see that the minimum activation count that is needed to induce the first RowHammer bit flip in a DRAM chip or in a DRAM row got reduced by more than an order of magnitude in less than a decade. So things are getting much worse here. And so there are many solution proposals in the literature. When we look at an example of them, which is called probabilistic row activation, we see that as the DRAM chip density increases and RowHammer vulnerability gets worse, we need to perform preventive refresh operations more aggressively, and it causes a significant performance degradation again. So with this problem definition, I'll move to our goal and key idea. Our goal is obviously reduce the performance overhead of DRAM refresh for both periodic and preventive refresh operations. And to achieve this, our key idea is to hide the refresh latency by refreshing a DRAM row concurrently with activating another row in a different subarray of the same bank. So I will explain in detail how we implement this key idea by proposing a new operation called HiRA, hidden row activation now. So the key inside of HiRA is the following. So when we activate two rows in current off-the-shelf DRAM chips in quick succession, if these rows are in different subarrays of the same bank, we end up refreshing one row concurrently with activating another row. Okay, so what does that mean to refresh? Okay, yeah, I will first mention the key benefits of this operation, and then I will dive into details how it works. So, so here we want to refresh row A, let's say, concurrently with activating row B, and assume that these two rows are located in the same DRAM bank, but in different subarrays. So if we wouldn't have HiRA, I will show how it works in a timeline. So we would first activate row A and wait for the latency of row A's refresh, and then pre-charge the bank and prepare the array for the next row activation, which is the pre-charge delay here. And then we would activate row B and then wait until the data is fetched to the row buffer so that we can access the data to read. So this is the latency we would observe. So when we do the same operation using HiRA, we send a sequence of activation, pre-charge, and activation command sequence in quick succession. So here, the first activation initiates row A's refresh, and without waiting, so we don't need to wait for this process to complete because we overlap the latency. So the second activation initiates the activation of row B. And once row B's data is in the row buffer, we can actually issue the read command. And by doing so, we can save this much of time. So now I will go through this HiRA operation in a little bit more detail. So here again, you see a DRAM. So you see a DRAM bank here with two different subarrays and two different rows in different subarrays. And we will see how it works on a timeline. So when we send a row activation to targeting row A, what it does is basically it connects row A. I hope you can see my pointer. Is my pointer visible? I think so. Okay. So it basically connects row A to the local row buffer in subarray X, and it starts connecting this local row buffer to the bank's I/O. And what we do basically by issuing these commands in quick succession is to interrupt this operation before this local row buffer X is connected to bank I/O. So when we interrupt this, our hypothesis is that this row A stays connected to the local row buffer in subarray X, and but this local row buffer is not connected to the bank I/O. And before precharge completes, again, we send another row activation so that this row is not closed. It is still connected to this local row buffer. But now we activate another row in another subarray, which connects that row to its own local row buffer, and also connects this local row buffer to the bank IO. And we call this operation HiRA, basically. And then after a while, once this data is completely connected to this bank IO, we can perform read operations, let's say, from the bank IO that contains the data of the row B. And then after a while, we send another precharge command. And this time we don't interrupt this precharge command so that it closes rows. And when we look at the restoration latency, so that row A experiences, it is this much, T restore A. And restoration latency of row B is also here. And you see which latencies are overlapped here. And by doing this operation, we hypothesize that HiRA refreshes row A concurrently with activating row B. And to do so, again, it just issues activate precharge, activate command sequence in quick succession. So this is a hypothetical circuit that makes HiRA possible. And as the next step of this paper, we actually show that HiRA is supported by real DRAM chips. So to do so, we use a modified version of SoftMC on an FPGA-based setup. We use Xilinx UltraScale Plus XCU 200 FPGA here. Yeah, we connect our DRAM module and we control the temperature of DRAM module by pressing two heaters on both sides. And we also have a temperature controller that actually provides us the fine-grained control on the chip temperature. And we have a host machine that creates this test command sequence, basically, and sends that to FPGA. And I assume that in the previous sessions of this lecture, you already saw how SoftMC works, how the ISA is for DDR4 setup. So we are basically using what you see already. This setup basically gives us a fine-grained control over DRAM commands. We can precise the time with a granularity of 1.5 nanoseconds when and which DRAM commands should be issued. And we have a highly accurate control on temperature. So in this work, we observed that HiRA works on 56 off-the-shelf DRAM chips from SK Hynix. Unfortunately, we didn't see a successful operation on DRAM chips from other manufacturers. But SK Hynix is already one of the the three major manufacturers, and they have already a large market share. So there's a chance that you can end up having one of these DRAM chips when you go buy some DRAM module randomly. So I will not go into details about the numbers that you see in this table, but I will highlight a few other numbers. So the first one is we look at for which particular rows we can perform this HiRA operation. And it turns out that you can refresh a row A concurrently with activating a row B if you choose this row B from any of the 32% of the rows in DRAM bank. So you have like 32% of the rows in a DRAM bank that you can parallelize, you can choose to concurrently activate with a refresh. Another result is that when we perform this HiRA operation and overlap the latencies of refresh and row activation or row access, we reduce the time spent for refresh operations by 51.4% reduction. And we conclude that HiRA effectively reduces time spent for refresh operations in off-the-shelf DRAM chips. So we are not sure how, basically we do not know how this operation is exactly supported in current off-the-shelf DRAM chips, but we have this hypothetical circuit that I explained a little bit earlier. So you can find more detailed experimental results in the full paper, as well as more information about the particular DRAM chips that we tested. And now I will move to the mechanism that we designed to perform these HiRA operations. The main goal of HiRA memory controller is to leverage HiRA's parallelism as much as possible. And it is based on the key insight that we need a time slide to find an opportunity of parallelizing a refresh with a row activation. So I will explain on a timeline again. Let's say you need to refresh a row A, and this refresh request is generated at this point in time. So basically what we do in this mechanism is that we generate these refresh requests with a time select earlier than when they need to be performed. So there is a time select between this time that is generated and its deadline. It's the time, by that time we need to perform the refresh operation for ensuring reliability. And during this time select, the memory controller can activate multiple rows basically. And for the sake of this experiment, let's assume that this row A and this row Z are in two electrically disconnected subarrays so that they don't share any subarray, any sense amplifier or bit line. What this mechanism does is basically it just replaces this activation command targeting row Z with a HiRA operation targeting both row A and row Z. And by doing that, it basically overlaps the latency of refresh with the row activation. So we implement all the necessary components in the memory controller to generate each periodic refresh and RowHammer preventive refresh with a deadline, with a time slide. And to buffer these refresh requests and perform the refresh requests until their deadline. And to find if we have an opportunity of concurrently performing a refresh with a row activation or with another refresh. And I will not, again, go into details for saving time, basically, about this mechanism, but you can find more details about the exact implementation of this mechanism. So I will just share some performance evaluation results. So we implemented this mechanism on a cycle level simulator called Remulator. This is a simulator that we use very frequently for our studies, things like for evaluating mechanisms and conducting performance evaluations. And we simulated a realistic system here, basically. That we don't need to go through some details, but you can see more details in the table and in the full paper. So in the simulation, we simulated 125 different 8-core multi-program workloads from this SPEC CPU 2006 benchmark suite. Excuse me. So we sweep DRAM chip capacity from 2 gigabit up to 128 gigabit for looking into future. And we also reduced RowHammer threshold from 10,024 activations down to 64 activations. And to remind what RowHammer threshold is, it is the minimum number of row activations that you need to perform in order to get RowHammer bit flip. So these are the results for HiRA for when we use HiRA for periodic refreshes. So here on the x-axis, you see the RAM chip capacity, and on the y-axis, you see the system performance in terms of using the metrics weighted speed up. And we report these performance results normalized to no refresh. So in the baseline, we do not perform any refresh operation. So the refresh overhead is 0. And we compare our results to auto refresh, which is the mechanism implemented in current DRAM chips. They use the conventional ref command, which is optimized for performing these refresh operations in an efficient way. So we observe that when we increase DRAM chip capacity, these periodic refreshes can cause significant performance overhead. And when we perform this refresh operations using HiRA, we can actually improve system performance significantly. Here again, you see a similar plot. So on the x-axis, this time we have the RowHammer threshold, which is the minimum number of activations you need to perform to get a RowHammer bit flip. And on the y-axis, now this time we have the system performance again in terms of weighted speed up, but now it's normalized to no defense. So in no defense, we don't have any RowHammer mitigation employed. So it is basically a system which is not really secure against RowHammer attacks. And it does not perform any preventive refreshes. So we compare our benefits to Para. We choose Para for this study because it is the RowHammer defense with the lowest hardware overhead, which we find the best candidate for scaling down for this kind of extreme RowHammer thresholds that we might see in the future DRAM chips. And when we look at the performance values here, we see that Para can significantly reduce system performance as it needs to aggressively perform row activation, probabilistic row activations. And when we replace Para's row activations with HiRA operations, again, we have slowdowns, but compared to Para, we can significantly improve system performance. So we have more analysis in the paper. First, we have real DRAM chip experiments to verify HiRA's functionality and how HiRA's functionality and behavior varies across different DRAM banks. We look at the HiRA's sensitivity to the length of time select for refreshes. So we sweep basically that time select parameter. And we look at how HiRA performs in memory configurations with varying number of channels and ranks. We have a hardware complexity analysis where we basically show that HiRA memory controller is a low-cost mechanism, and it does not induce any additional latency to access these structures. And we provide more details about our experimental methodology, including detailed algorithms that we run for in the soft MC setup, basically, when we test the real DRAM chips. And also we include an extensive security analysis for RowHammer preventive refreshes, which basically revisits Para's security guarantees, security analysis, and makes it more robust, or let's say addresses a stronger threat model basically for reducing RowHammer threshold. And we also present a detailed algorithm of how we find concurrent refresh operations in a short amount of time. So I will again refer you to the full paper for more details. And to conclude, we propose HiRA in this paper, which is a new DRAM operation, and long name is hidden row activation. It is the first technique that refreshes a DRAM row concurrently with activating another row in the same bank in off-the-shelf DRAM chips. Based on our real DRAM chip experiments, we showed that HiRA works on 56 real off-the-shelf DRAM chips. So we can find more chips, of course, that supports this. And it reduces the time spent for refresh operations by 51.4%. And HiRA, to effectively use HiRA in future systems, we also propose a memory controller-based mechanism called HiRA memory controller. And it leverages HiRA to perform refresh requests concurrently with DRAM accesses and other refresh requests. And HiRA memory controller provides significant speedups by hiding both periodic refresh latency and the latency of RowHammer preventive refresh operations. So yeah, this is the paper, and I think this concludes my talk. I'm happy to not ask yet, any questions you might have.
Thanks, Giray. It was a really good presentation, and there are no questions on YouTube chat. I might try to ask something. Well, let's see how it goes. So I think that it's really good that this allows you to parallelize refreshes in a sense with useful commands like activation and read and write. Do you think that it will be even more important as RowHammer threshold reduces and we have to perform these refreshes for even longer amount of times? And do you, I guess, do you have any ideas if HiRA can be even better in that sense, in reducing the overhead of refreshes?
So I guess I will go back to this results basically, because as we reduce RowHammer threshold, we need to perform row activate preventive refresh operations more aggressively, right? So I don't know if this addresses, your. I'm not sure if I understand. So when we overlap these latencies, we greatly reduce the latency overhead of performing a preventive refresh. And if we need to perform these preventive refreshes more aggressively, then the overhead is huge, and we can reduce it to some extent. I think this parallelism is important.
Yeah.
I don't know.
Yeah, from this slide, I see there's like a huge headroom, maybe 37x speed up on top of a baseline para design, I guess, so that you can go back to no defense speed ups. Yeah, I guess there's a lot to improve over there, right? Yeah,
so it can be possible if we can actually fully leverage the parallelism we have across subarrays. So, well, it's a tricky sentence actually. So, when we look at the, okay, maybe I should talk about this slide a little bit for the larger audience. So in a DRAM bank, we have multiple subarrays, right? And each subarray has their own row buffers, word lines, bit lines. So essentially, these subarrays are actually can be used independently from each other in theory, right? And there are some prior works from our group. Again, I'll refer to like SALP and DSARP. So those papers are actually showing that if you can leverage this already existing parallelism across subarrays by like, okay, you perform a row refresh in a subarray, and you can fully overlap the latency of that refresh with like accessing another subarray or refreshing another subarray. And if you can do that, yes, maybe you can reach the performance of no defense because you can hide all the preventive refreshes for RowHammer. Yeah, so far we have this parallelism in real chips, but we at the same time we don't have, because the JEDEC standards basically do not allow us to perform activations or refreshes to different subarrays in the same bank in a fully overlapped manner. And I think we need to revisit like raw decoder design, just like those papers do. And we don't know how it is designed in the current chips at the same time. So yeah, there are some challenges about like syncing up with the industry in that sense. I don't know.
Yeah, I think what you said makes sense. And it's like possibly a good research direction. But anyways, there are no more questions from me. So I guess you're done and we can end this live presentation.
Okay, yeah. I hope it will be useful for yeah, the students and whoever is watching on YouTube.
Yeah. Thanks, Giray.